Exercise 6F, sine and cosine graphs. What we have here is a table of values. We have angle theta, and that's varying between -2 pi and 2 pi. And we take those angles and we work out the sine of those angles in this next row, sine of theta, and you can see the values produced here. These values have been produced just using a CAS calculator. So for example, I've literally just put into my CAS calculator sine of -2 pi, and that produces 0, and I put that into the table. If I were to take those values and place them on a set of axes, graphically it would look like this. And you can see it's a wave shape, so it's our wave pattern, and it goes on indefinitely towards the right and indefinitely towards the left. If I focus between theta equaling 0 and 2 pi, you can see I begin at the position 0, 0. I then move to the position pi on 2, 1, then back down to pi, 0, 3 pi on 2, -1, and then back to 2 pi, 0. So that pattern will go on forever. And in the same way, I can also take a look at cosine. So once again, a table of values. Using my CAS calculator, I can produce the corresponding cos of the given angles. Graphically, it looks fairly similar. It's a wave shape again, but the pattern form is a little bit different. You can see once again, if I begin between 0 and 2 pi, in this case I start at the position 0, 1. I then move down to pi on 2, 0, pi, -1, 3 pi on 2, 0, and 2 pi, 1. So they are the sine and cosine graphs, and they are closely related to the unit circle. So if we go and take a look at the unit circle, so here I have the unit circle. Remember, it has a radius of 1, and I have a point P. Remember, this point P can be described as being x, y, but equally it could be described as being cos theta, sine theta, where theta is the angle swept in between the ray and the x-axis, so it's this angle in here. Alright, if I now turn on the sine function, you can see here's my sine graph to the right hand side of it. So basically all I've done here is that you've got a vertical axis ranging in this case between -2 and 2, and then horizontally what we've got is the angle theta. Now this is given in degrees, but it could easily be in radians, so you can see here 0, pi on 2, pi, 3 pi on 2, and then 2 pi. And I can make this point P move around the outside of this circle, and we can see what sine of that angle theta is equal to. Remembering that if this point P can be described as being cos theta, sine theta, it's quite clear to us that the y value at this point is going to be equal to the sine theta. So you can see in this certain position that whatever this reads off to be on the y-axis of the unit circle is also what's equal to sine of that angle theta, this theta here, which is unknown, or in fact it is known to us. It's 34 degrees. So sine of 34 degrees is equal to exactly 0.5592. So what we're saying with that is that this position along over here where it cuts through would be 0.5592, and that in the same way that sine of 34 is equal to 0.5592. So let's take a look at the animation. So here you can see that the dot is approaching pi on 2, the value of y is approaching 1, there we are, you can see that graph. Now as theta gets towards pi, you can see the value of y is approaching 0. Theta continues and we're approaching 3 pi on 2, and the value of y will be approaching -1. It's a sine of that is -1, and then we've almost done one full revolution getting towards 360, and we're complete just now, a little bit over, but you can see there that we've done one full cycle of the graph, one full revolution of the unit circle. I can continue on and apply the cosine on top of it, so there's a cosine on top, and let's just take a look at one full revolution of the cosine, one full revolution of the unit circle. Let's turn off the sine and hit start, and you can see the two dots. Of course now we're looking at the x value, so As the p is approaching pi on 2, the value of x is approaching 0. And now p is approaching pi, and the value of x is approaching -1. P is approaching 3 pi on 2. The value of x is approaching 0 again. And as we approach 2 pi, the value of x will be approaching 1. Beautiful. Okay, so that shows you the relationship between the unit circle and the sine and cosine graphs. Going back to our notes, so there's an explanation of that. A couple of really important points for us to understand is the period and the amplitude. So the period is just basically how long it takes for the graph to start to repeat itself. So if we begin from this position here at 0, 0, you can see that we do one full cycle, and it takes us 2 pi radians until the cycle begins to repeat itself. So we can say there that the period is equal to 2 pi. You can see it's a distance, the same distance between the two peaks here. Alright, so here I'm at the peak, and then I finish off at the peak over here, and the distance in between that is 2 pi. The amplitude is just the measure of the size of the wave. Okay, so we don't measure from the trough to the peak, we just measure from what they call the median to the peak. Okay, so the general standard form is an amplitude of 1. So basic graph, so if we had the basic y equals a sine of nx and y equaling a cos of nx, then the amplitude is a. That's assuming that a is positive. Of course, if a was negative, then it would be just the magnitude of that. So in other words, we're looking at the size of the a value and not the sign of it. The period is 2 pi on n, where n is the coefficient of x. If n is less than 1, the graph is effectively stretched horizontally, so it's drawn out. If n is greater than 1, then the graph is effectively compressed. So we're taking the wave and we're pushing it in tighter. If a is less than 1, the graph is compressed vertically. Okay, so we're looking at, along the y-axis, we're looking at contracting it. And if a is greater than 1, then we're stretching it out. The way that we describe the effect of this is that we say that A we can describe as being a dilation factor of A parallel with the y-axis, that is, it is from the x-axis. So in other words, we take every y value of the points and we multiply it by A. And we say that we also have a 1 on n parallel with the x-axis. So in other words, what we're doing there, guys, is we're taking the value of the x of every point on the original graph and we're multiplying it by 1 on n. Alright, here we have a problem. Sketch the graph of the function. We've got f, given that we go from 0 to 5 pi on 3. Notice it's circular bracket, so that means that we're not including where x is equal to 0, but we are including 5 pi on 3 because we have the square bracket. So the domain is between 0 and 5 pi on 3, and we can have any real number that's been produced from this rule here. F of x equals 2 lots of sine of 2x on 3. And we have to state the range of the function at the very end. To help us understand that, it's probably always good to work out what the amplitude is. So it's just going to be the magnitude of 2, so that's that number in the front there, which is 2. So it gives us an idea of how wide the wave will be. Sorry, how tall the wave will be. Our period is 2 pi on n. Now n is just the number in front of the x, so we can think of this number as being 2 on 3 times x, so 2/3. So 2 pi over 2 on 3 is the same thing as getting 2 pi and multiplying by 3 on 2, and we see that it's equal to 3 pi. So in other words, one full wave will be completed as theta goes from 0 to 3 pi. That's how long it will take. Describing the transformations is always a good idea, just to get our heads around what's happening. So first of all, it's dilated by a factor of 2 parallel with the y-axis. So that's given from this 2 here. So that just means that every y value on the original y equals sine of x has been multiplied by 2. Also, we see that it's been dilated by a factor of 3 on 2 parallel with the x-axis. So what this tells us is that every x value on the original graph has been multiplied by 3 on 2. Effectively, it's been stretched. When I'm graphing this, I like to use a bit of a T-grid method. So you can see here on the left-hand side, I've put down all the critical values for the basic graph, the basic sine function. So I've got 0, 0, pi on 2, 1, pi, 0, 3 pi on 2, negative 1, and I've got 2 pi, 0. So that's my x's, well they are my x's, and these are my y's. And then I apply the transformations on them. So first of all, a dilation factor of 2 parallel with the y-axis, so I'm getting all these y values, and I just got to multiply by 2, and that will create these values over here. The next transformation I need to take care of is dilation by a factor of 3 on 2 parallel with the x-axis. So I take the x values and I multiply those by 3 on 2 and I get these results. And then it's a matter of placing these down for the x's and this column here for the y's, placing those on a set of axes, and which I've done just here. Whoops, as you can see, just there. So these are the 5 critical points which I've found, and I've placed them, and I get that nice wave shape as I expect. But what I do need to do is take in consideration the endpoints. So first of all, the domain on the left-hand side, I start at 0. So I plug in 0 into the rule, and I get 0, which is not a big surprise. So the point 0, 0, and I notice that because in the original domain, just giving up the top here, in my original domain, 0 is not included in the domain. So I should see a circular point there, a hollow point. Okay, so that's 1 point, that's excluded. The included point is 5 pi on 3, so I substitute 5 pi on 3 into the rule, and I get 2 sine 10 pi on 9, and that point is included. So getting back towards my graph, I've drawn it with the endpoints. Now, you might be sitting there asking, how is it that you know that 5 pi on 3 is somewhere around here between 3 pi on 2 and 9 pi on 4? Whenever dealing with radians in this type of problem, I always try and think of making it easier for me by converting it to a decimal. So 3 pi on 2, for instance, I can think of as being 1.5 times pi. 9 pi on 4, I can think of as being 2.25 lots of pi. And of course 5 pi on 3, I can think of as being 1.67 lots of pi. So 1.67 lots of pi is somewhere between 1.5 lots of pi and 2.25 lots of pi. So I can safely say that it's somewhere along this section. And if you were to evaluate what 2 sine of 10 pi on 9 is, you'll see that it comes out to being a negative number. A really big point here, guys, in this type of question, it's not really critical for you to show all the workings that I have. Okay, what you will be graded on or judged on is how well you've drawn this graph and that you've shown the endpoints. It may be a good idea to show the workings to calculate the endpoints, but at no stage will you be assessed on how well you've set up a table and whether or not you've written down the transformations. It's simply there to help you get to that graph. The graph is what you're looking at with the calculation of the endpoints and the endpoints clearly shown. As you become better at this, then you become more efficient and you won't have to write as many details. But as always, when I provide solutions to problems, I'm doing it in such a way that you can go back into your notes and it'll make sense to you. But a part of the question was asking us for the range, okay? And with our range here, you can see that the lowest value included in the graph that we need is over here. So that lowest value is 2 sine 10 pi on 9, and then the highest value we achieve is 2. So I'm going from 2 sine 10 pi on 9, that's the lowest value, and that ends up being a negative number if you were to get an approximate answer for it, going all the way to 2. And notice that I'm including the 2. All right, so I do actually include this position here. So I am including the 2, and I also include this. The standard graph of sine is y equals sine of x, but we can have variations of that. Consider this case, y equals capital A sine of the bracket n multiplied by x minus h plus k, and we have the same kind of effect taking place with the cosine. But what is it that capital A, n, h and k does to the standard graph of sine and cosine? Well, let's look at capital A to begin with. We say that we have a dilation by a factor of the magnitude of A parallel with the y-axis. That is, it's from the x-axis. So in other words, we take the y values of the standard graph and we multiply it by the size of A. Remembering that the magnitude of A just means that we're looking at the size of that number. We're ignoring the fact whether it's positive or negative. If the magnitude of A is less than 1, then the graph is effectively compressed vertically. So that means that the height of the wave is reduced, so it becomes shorter. If the magnitude of A is greater than 1, then we take a look at the height of the wave and we make it taller, it's stretched vertically. If A itself is less than 0, so that is if A is a negative number, then the graph is reflected in the x-axis, so it's just flipped around that x-axis. What's the effect of n? We say that we have a dilation factor of 1 over the magnitude of n parallel with the x-axis, or in other words it's from the y-axis. So in other words, we take every x value of the standard graph and we multiply it by 1 over the magnitude of n, 1 over the size of n. If n itself, if the magnitude of n is less than 1, then the graph is effectively stretched horizontally. So if the magnitude of n is less than 1, so it's a fraction, then it's stretched horizontally. So in other words, what we're seeing there is that we take the wave and we stretch it further out wider across the x-axis. If n is greater than 1, then it's compressed. So we take the wave and we push it closer together. If n is less than 0, so the actual value of n is less than 0, then it's reflected in the y-axis. The effect of k, so this is really easy for us to understand, the effect of k. If k is less than 0, then it's shifted down, so if k is a negative value, it's shifted down. If k is a positive value, then it's shifted up by k units. The effect of h, remembering that we've got the format of this graph into this shape here. Okay, so this is the format that we've got it in, n multiplied by x minus h. Then the effect of h will be that it moves it left and right. As always, I suggest that you take whatever this stuff is in the square brackets, you make it equal to 0 and you solve for x, and that will tell you exactly whether you're moving in the positive direction or the negative direction and how much by. I think it's much easier to understand the transformations in that way. The amplitude is simply equal to the magnitude of A, that value in front of the entire sine or cosine function, so this value here. The period is 2 pi on the magnitude of n, so that tells us how long the wave is, how long it takes to complete one full cycle. The median is k, so usually in the standard graph the median is 0, but we're looking at that vertical translation, that's what the k does, and so the k value tells us that middle value of the wave. The maximum is going to be k plus the amplitude, and the minimum is going to be k minus the amplitude. Alright, so that basically describes the transformations and the effect of h and k for the basic sine and cosine graphs. As I've stated earlier, the steps that I follow to sketch sine and cosine graphs are these here, these 5 steps. I begin by ruling a wide T-shaped grid and putting the critical points for x and y vertically down the grid. So for sine, these are the 5 critical values I'd put in, and for cosine, these are the 5 critical values I'd put in. I would then jot down the transformations in DRT order, so dilations, reflections and translations in those orders. I would then apply the transformations on the x and y values, working in DRT order from inside the grid, working my way to the outside. I make a good point here in 4 saying that when dealing with fractions, it may be easier to add columns for workings instead of trying to do the calculations mentally, because calculations can be quite complicated, and it's easy to make a mistake if you're trying to do all the processing in your head. And finally, I just plot the 2 outside columns. I plot those on a set of axes, and just be mindful of what the domain is so that you answer what you need to. Let's look at how this works in this particular problem. Sketch the graph of y equals 3 lots of sine, 3 lots of sine of 2x plus pi on 3 minus 5, and state its domain and range. What I notice is that I can manipulate this equation so that the coefficient of x is a 1, and I can do that by taking 2 out of the bracket. So if I have 2x and I divide it by 2, I'm going to get just x, and if I have pi on 3 and I divide it by 2, I'm going to get pi on 6. So you can see that this line here is exactly equivalent to this, but it's in a format that I can easily work with. So y equaling 3 lots of sine of 2x plus pi on 3, take away 5, is the same thing as this line here. Alright, stating the transformations. I notice first of all that I have a dilation factor of 3 parallel with the y-axis. I have a dilation factor of a half parallel with the x-axis. I'm shifted 5 units down, and I'm shifted pi on 6 units to the left. So pi on 6 units to the left. So it's the opposite of that, remembering that the easiest way of working this out is to simply take it, make it equal to 0, solve for x, and you'll see that x would be equal to negative pi on 6, so that tells me I'm moving in the negative direction, i.e. to the left, by pi on 6 units. So there's my transformations, and I'm going to use these transformations or knowledge of these transformations to help me do up the grid. So here's my T-shaped grid. I just first of all rule up a big grid, and there's my vertical. I plot in the critical values for x and y, and these are the critical values for the standard sine graph. I then start applying the transformations. So dilated by a factor of 3 parallel with the y-axis, so I'm multiplying every y value by 3, and they're the corresponding values. Dilated by a factor of half parallel with the x-axis, so I take the x values and I multiply them by a half. Here they are. Translated 5 units down, so I take this result and I subtract 5 from it. And there are my final y values that I'll put on my axes. And translated pi on 6 units to the left, so I subtract pi on 6 from the x values. So I'm subtracting pi on 6. Notice that my next column is just basically trying to get everything together in a way that makes sense to me. So what I've done is I've converted everything to being over 24. I've then tidied it up so everything here is over 24. And you'll notice that they're equally distanced apart. Basically, as I go down, I'm growing by 6 pi on 24 units. And there's that pattern, and then I've simplified those. Now what should be pointed out here, guys, is that it may not be necessary for you to show all of these columns and all these workings. You might be able to just do that in your head. And if that's the case, that's great. That will save you some work. But this guarantees that you'll get the right answer. What I should also point out to you is that it's not always necessary to write down all these different transformations here. Okay, so they are my table of values. I'm going to work with this last column here and the very first column on the left hand side, so the 2 outside columns. So I rule myself up a set of axes, as you can see here, and it's just basically plotting those positions, which I've done. And notice, because there's no domain restriction, I've drawn arrows showing that the graph goes on indefinitely in either direction. I was asked to state the domain and range. So the domain is R, set of all real numbers, so it can go on indefinitely. And the range, my lowest value that I have for y is -5, and the highest value I have is -2, and I am including those, so they're written with square brackets. So it's quite simple. All of the workings I've shown you, you don't need to show me everything like this. What you will be looking for, or what I will be looking for, in fact anybody assessing your work will be looking to see that you've ruled up your axes correctly, that you've shown the wave, and that you've stated domain and range appropriately. The rest of it are just working so you can get to there efficiently. If you can do some of that working in your head, that's great. Certainly you don't need to write the transformations as formally as I do. Perhaps you just need to jot down a few different ideas. You certainly won't be graded or looked at in the way that you've worked any of this part out. I'll cut that.